Okay, so now to start the test, we're going to take partial derivatives of this original equation, which I've copied over here. It's 4 plus x cubed plus y cubed minus 3xy. So the first partial derivative that we're going to take is in respect to x. So the 4 would go away, and then the x cubed would turn into 3x squared. And then the y cubed, we're not taking it in respect to y, so we can forget about that. And then minus the 3xy. So we're going to do minus 3y because the x would go away. And then for the other one, we're going to do the same thing, because it's in respect to y, we're only going to factor the y values. So it's 3y squared minus 3x. And we're going to set these equal to 0 to find the critical points. So for this one, we can do 3x squared equals 3y. And this one can be 3y squared equals 3x. Now we can divide both of these by 3 and get x squared equals y. And the same with the bottom. And get y squared is equal to x. So now to solve this systems of equations, we can put one term in for the other. So y is equal to x squared, so we can put the x squared in for this and do x squared equals x, or x to the 4th minus x equals 0. So to factor this out, we can take one x out of it and do x cubed minus 1 equals 0, and then we get the x equals 0, and x cubed minus 1 equals 0. For the x cubed minus 1, we add the 1 over, and then we end up with x equals 1. So our two x values are x equals 1 and x equals 0, and we'll plug those back in for y. So 0 squared equals y, which would make 0 equal to y. And 1 squared equals y, which would make 1 equal to y. So our y values corresponding to the x values are 0, 0, and 1, 1. So we found that the points that we had originally thought here, which we said was about 1, 1, and this point that we said was 0, 0, were accurate. Now to find out what kind of points these are, we're going to try the second partials test. So we're going to take the second derivative of these. So d squared z over dx squared, which in respect to x would just give us 6x, and the d squared z over dy squared would give us 6y. So then we need to just plug in our values and add them together. So we would do 6x plus 6y, which would be, for the point 0, 0, would be 6 times 0 plus 6 times 0, which would be equal to 0. And for the point 1, 1, be 6 times 1 plus 6 times 1, which is equal to 12, which is greater than 0. And that's the thing that we were trying to find. Because this is greater than 0, it means that this is a concave up function. And because it is concave up, that means that it would have to be a local minimum. Because remember, when you have a concave up function, it could look like this. So this is the critical point that we have, and because it's concave up, or how I like to remember it is in a smiley face, it's smiling up, then it has to be the minimum because this is a low point. For it to be the maximum, it would have to be concave down, or like a frowny face, because then the critical point would be up here. So this is what we have. We have a minimum at this point 1, 1. And because it is equal to 0 here, it is neither concave up nor down, which leads us to believe that it is a saddle point, which is what we had originally discussed over when we looked at the graph here, because of the fact that it was across and that it seems to be going down as we go into it here, but increasing as we go into it here. So that was what kind of gave it away, that this way it was increasing, but this way it was decreasing. So now that we have an understanding of the question, I'm just going to do one more thing. I'm going to show the calc plot, the 3D calc plot version of this graph, just so that we can see in a 3D version what it looks like, and we can look and see the actual minimum and saddle point values that we found.